Hi, while scrolling through the internet, you might have came across these kinds of videos in which this object seems to be floating in midair, almost like there is some kind of magical force involved. But is there any? Well, I have also searched through the internet and found out the reason behind it. Spoilers alert, there is no magic here. It's pure physics in all its beauty. This is a superconductor, and superconductors have been changing our world like crazy. Have you ever heard about magnetically levitating trains? Trains that go on the tracks like normal trains, but they are floating above the tracks, and their speeds are so high that they can cover 600 kilometers in just an hour. Imagine such a high speeds achieved, and that too with low power supply, like these consume very less energy to run on. Also, if you pass the current through the superconductors, it will keep on flowing for thousands of years without need of external energy source. And why is this such a big deal, you ask? Because if superconductors are used to conduct electricity, then there will be no bills at all. Energy will be completely like free because current will keep on flowing without need of external energy source. All these things got me curious to know more about superconductivity. If you are curious too and you want to know what is superconductivity, I am Jyoti Sharma here, and you have started watching Achieve It with Jojo. And in this video, we are going to cover superconductivity. We will discuss what is Meissner's effect, and we will discuss the theory that is given to explain the concept why some conductors behave as superconductors, why some materials would be more appropriate to say behave as superconductors. So let's start with superconductivity. What is superconductivity? When you cool down some materials to very low temperatures, then they start to conduct electricity as if there is no resistance there, absolute zero resistance. This phenomena is called superconductivity. In 1911, Heike Kamerlingh-Onnes, a Dutch physicist, was conducting a series of experiments in which he was trying to cool down materials to very low temperatures. In this series of experiments, he also cooled down mercury to very low temperatures, and then he passed electricity through the mercury, and to his shock he found out that resistance was almost gone. There was no resistance there. This was the graph which was obtained when he plotted the resistance versus temperature graph. Here you can see, as the temperature is around 4.4 Kelvin, there is some resistance present in mercury element, but when it decreases, when he tried to decrease the temperature, resistance started to vanish, and at 4.2 Kelvin temperatures, resistance was completely vanished. There was some resistance, but it was very negligible, so it was practically gone. The temperature at which normal conductor behaves as superconductor, that is its resistance is completely gone, is called critical temperature of superconductors. Below the critical temperature, material behaves like a superconductor, and above the transition temperature, above the critical temperature, superconductor behaves as normal conductor and doesn't show any specific properties that superconductors do. So now the question arises, are all the elements in the periodic table capable of becoming a superconductor if they are cooled down to very low temperatures? The answer is no. Look at this periodic table. Here are some materials that are capable of becoming a superconductor if cooled down to their transition temperature, and below the transition temperature they show superconductivity. Like for example, we were discussing about mercury. Here is mercury, and it shows the transition temperature around 4.15 Kelvin, which is precise. Earlier we were talking in the terms of around, like 4.2 around, but this is the exact number, 4.15 Kelvin. And as you can see, lead it shows superconductivity at the transition temperature of 7.2 Kelvin. Transition temperature means below this temperature this material will behave as a superconductor, and above this temperature this will behave like a normal material. And with this cyan kind of color are those elements that show superconductivity only at high pressures. So pressure should be high in order to make them behave like superconductors. So if you notice, these elements show superconductivity at very, very low temperatures, but for practical uses we need superconductors to be used at room temperature about 300 Kelvin. But I can't see any of these showing superconductivity at room temperature. So what's the solution? So scientists have found out various other materials which, like these materials, which show superconductivity at different temperatures. This is an overview. Science evolves when scientists decides to do experiments with the previously known knowledge and adding something new to it. Two German physicists did exactly that. They cooled down lead and tin below the transition temperatures and see what's going on, but this time they applied magnetic field as well. To their surprise, magnetic field that they observed, the magnetic flux that they observed, was showing something different. What Meissner observed was the complete expulsion of magnetic field from the superconductor. This Meissner effect can also be understood with the help of this image. Look at this image. In this image, there are two blue spheres. These both are representing some material. And these lines, these black colored lines, are representing the magnetic field. And the direction of magnetic field is from bottom to up, as this vector is showing. So when the temperature of the material is above the critical temperature, now we are very familiar with what is critical temperature, the temperature at below which the material behaves as a superconductor and above which it behaves like normal material. So here on the left side of the image, this material is behaving like normal material. It is letting magnetic field lines pass through it. But on the right hand side, as soon as the material enters into the superconducting state, then it expels the magnetic field. It kinds of bends, these magnetic field lines bend around the material, and this is the reason, this Meissner effect is the reason that we see magnetic levitation, the one which we showed at the start of the video and this one as well. So this is pretty cool effect if you see from science fiction kind of lenses. Okay, that's good, but wait, we can vary the strengths of magnetic field as well. Like we can apply the magnetic fields with huge electromagnets or huge magnets which have very high magnetic field strength, and we can also use these tiny fridge magnets as well. So is there any difference in this superconducting state of the materials, or things go as they are going? The answer is some things do change. Superconductivity will get destroyed if you apply huge magnetic fields, and the upper bound up to which magnetic field can be applied and the superconductivity remains, that is a material behaves as superconductor, is called critical magnetic field. Like critical temperature, there is also a critical magnetic field as well. As you can see from this diagram, this blue line is depicting the magnetic field which can be applied. Below this curve are all the points and all the magnetic field values which kind of preserves the superconductivity. But if you go on other side of the curve, you can see that magnetic field will completely destroy the superconductivity of the material. So this critical magnetic field can be evaluated by using this formula. But why have I written magnetic field versus temperature for type 1 superconductors? Are there any other kind of superconductors, and what are the types of superconductors? Yes, there are two types of superconductors: type 1 superconductors, also known as soft superconductors, and type 2 superconductors, also known as hard superconductors. Type 1 superconductor shows complete Meissner effect. Below the critical magnetic field, superconducting materials behave in a superconducting way, and above the critical magnetic field they just behave as normal materials. In type 2 superconductors, there are two magnetic fields, two critical magnetic fields, which as you can see in this diagram, there is upper critical magnetic field Hc2, represented by this Hc2 and this red line, and there is lower critical magnetic field Hc1. And here this blue region is depicting the superconducting state. It is purely superconducting state, and this yellow part of the diagram is showing mixed phase, mixed state, like vortex state. In this, some of the magnetic field lines, if you can imagine in that way, are passing through the superconductor. Remember, in pure superconducting state, not even a single magnetic field line could pass through the superconductor, but in mixed state, some magnetic field lines could penetrate our superconductor. So these are two types of superconductors. Generally, type 1 superconductors are pure metals or pure materials like lead and mercury, and type 2 superconductors are generally alloys or complex compounds such as yttrium, barium, copper oxide, which is very commonly used nowadays as a superconductor. Now up to this point, we have got good idea about what is superconductor and what is Meissner effect, what is critical magnetic field, and what is critical temperature. But what about the resistance getting zero? How can a material exhibit zero resistance when there are so much atoms in the lattice, and when there are so many electrons? They must collide among themselves and produce heat and exhibit resistance to the flow of electrons. This answer was given by three scientists, Barden, Cooper and Schrieffer, in 1957, and the theory that they developed is popularly known as BCS theory of superconductors, of course. To understand BCS theory, let's first understand what's causing resistance in first place. Like at room temperature, what is the source of resistance? See, when for example we take a wire, and when electrons move from one end of the wire to another end of the wire, we call it like the current is flowing in the wire. But these electrons, it's not like these electrons aren't encountering anything in between and they have got it all smooth, all figured out, and it's not like a cakewalk for them. They are encountering many things in between. These electrons are colliding with other electrons, causing them to scatter, and they are also colliding with atoms that are already present in the material, and which is leading electrons to lose some of their energy, and this is causing hindrance in their motion. And this hindrance is what we call resistance, basically, that electrons are facing some kind of problem in moving from one part of the wire to another part of the wire, and what we call conduction of electricity. So what happens when we cool down the materials to very low temperatures? Below the critical temperatures, these lattice vibrations are minimized. That is, these atoms are not vibrating that much anymore, and these electrons have a smooth path to move into, kind of You can imagine it like that. And also these electrons don't move individually now, they form pair. Two electrons are now forming pair known as Cooper pairs, and this pair is already in very low energy state. And so if collision even happens, then which doesn't happens, but collision if even happens, then they don't have a state below the state to go into. So this is the BCS theory, that below the transition temperature Cooper pairs are formed, and these pairs are mediated by phonons. That means there is a electron phonon and electron interaction. Phonon are the particles associated with lattice vibrations. So this is the theory behind the superconductivity, although scientists are working on other theories as well. So this was all about the superconductivity, and of course the applications of superconductivity are way much diverse. They are used in maglev trains as discussed at the starting of this video. These are getting used in MRI machines. They are also getting used in quantum computing, and they are also used for energy devices as well. See you guys in the next video. Till then, enjoy learning.